All right. Hello to everyone who's joining us. We have had a bit of a break from these physics working live streams during our summer school and summer camp and other things, but now we are back. And today we're going to look at a project that I started doing around 1992 and have been meaning to get back to ever since. And that will turn out to have importance for both things we're doing in the physics project and some applications of the physics project to things like molecular computing. So the topic is tilings. And the question is something that I talked about in the NKS book. And the idea is you are making a tiling by saying that, let's see, I think I have better examples than this. Let's take a look. Well, the issue is if you say around every black square there are two white squares and two black squares, around every white square there are three white squares and one black square, what possible ways are there of covering the plane with those constraints? And sometimes there's a unique way to do it. Sometimes there are multiple possibilities, stripes and spots in this case. And sometimes there are no ways to do it at all. I'm not sure if that's the case here. Maybe, I'm not sure, I can't even tell if that means that there's no way to do it, or whether that means that that the only way to do it is, I think that means there's no way to do it in those cases, because I think this is the all white case. So this, I forgot my own notation there. This means there's no way to tile the plane then. Okay, so a thing that I found in NKS is if you look at around every given square, you say that only these neighborhoods of squares are allowed. The question is, what tilings are, in this particular case, with this set of neighborhoods around every square allowed? This is the only possible tiling you can get. Similarly here. And one issue is if I were to add another tile here, then immediately I have a choice of this tiling and potentially other tilings. So there's not a unique tiling, but there is always a unique minimal tiling. I think Ed may have a correction to that claim, that there is always a point as you look at the sort of hierarchy, the partially ordered set of possible allowed tiles. There will be a moment it goes from there aren't enough allowed tiles to tile the plane at all to the point where there are so many tiles allowed that there are many ways to tile the plane. But there is always a point of sort of first where you first have tiling. Is that true, Ed?
I don't have a counterexample yet.
But do we have a proof that it's true?
No, we don't have that either.
Okay, but so what we should see is essentially a, we could represent this by some kind of, partially ordered set, essentially a causal graph type thing of possible tilings, where it's one of these subset poset type things, right? Because how do you make the poset of subsets? You know what I'm talking about, Ed? Do you know what I'm talking about? The tree of subsets. Anybody know?
It's been a while.
Okay.
In the cases I'm looking at, all subsets do not tile, so they're not too interesting yet.
Well, wait. I'm sorry. The thing I'm asking is, given that you have the subsets of a given set, right? Okay, here. There is a partial ordering to these subsets, right? So in other words, this subset, the subset relation defines a partial ordering of these subsets.
Right.
Right? So what I'm asking for is, how do we draw the, there is a way to draw, and this must be very straightforward. There is a standard way of joining. Okay, so what we need to do is to say which of these are neighbors with respect to the subset Q, right? So each one, we need to ask for every given one of these, what other things are the what subsets do we get? And Joseph is commenting here that it's always a hypercubic graph. I think that's correct. But
Yes.
can we actually generate that graph?
Yes, but they get complicated quickly.
I know that, but I want to. Okay, that's the graph. Okay, the whole point is what we're trying to do is what should happen is in that graph, you should be able to color that graph according to whether a particular subset tiles or doesn't. Do you understand what I'm saying? So in that graph, there should be you're essentially foliating that graph with the question of whether the thing tiles or not. Does that make sense?
Mm-hmm.
Okay, so I just want to understand what that looks like. That is it the case that what you should get is something which is that graph, and then there'll be there's a sort of at the top it doesn't tile, and then it goes, or at the top, depending on what the top is. If the top is everything, it tiles a lot. But then there's a frontier where it starts to tile, right? So could we just draw this graph, please? Is there an easy way to draw this graph using nearest neighbor graph, for example? Do you understand what I'm saying, Ed?
Yes. With the 2x2 case, there's only 17 cases that matter out of 16 factorial possible cases. So
no. You're answering a different question. I'm simply trying to draw this graph for partial orderings in subsets. Okay? Can we figure out how to do that?
Graph data hypercube 5.
And why is this? I mean, that's trivial to draw. I can draw that in, let's see, how do I draw that? I just do grid graph, right? That's just a grid graph with that's just this grid graph,
Mm-hmm.
right?
Mm-hmm. Yep.
But why is that? So can I label this? Could I label it with the subsets here?
Yes, we could do, if something is a subset of another, we could do a order. It would be an ordered graph, basically.
Yeah, I know. So that's what I was asking.
I'll write that up quickly.
Okay.
Give me a second.
No, I think you can just tell me what to do, because this should be nearest neighbor graph. Look, actually, all we have to do is say for each of these, we just have to remove an element, right? Table of that list, whatever it is. Delete list I. I goes to length of list. And then we have to say list arrow that. And then we have to say that becomes flatten that. And then we have to say, essentially what we've got to do is just iteratively generate this thing, right? Yes, this is Richard on our live stream is pointing out this is a Hasse diagram. Yes, it's a Hasse diagram. And if we have something, and maybe we have something in the function repository for generating Hasse diagrams. Oh, look at that. What do you know? There is. Well, there we go. Thank you, Richard, for that comment. Okay, here we go. This is exactly what we needed, right? This is exactly the point. Okay, this is what I wanted. Yes, great, thank you. And that, yes, so what we're looking for here is in this diagram, right? Certain pieces, there will be a threshold at which tiling is no longer possible. Make sense? Okay. All right, let's go back.
Yes, it does.
Okay, thank you. All right. So now let's talk about what okay, so the big thing that has arisen since the time of the NKS book. At the time of the NKS book, hey, you're typing in one's ear. The way that I computed these tilings, we had this program that would basically do, go out in a spiral and keep, it would try a tiling and then it would backtrack if that tiling didn't work. The approach now is to basically build a Boolean expression and simply use satisfiability testing to find an instance find a satisfiability instance. So this thing is turned into a Boolean function. I think I have an example of that someplace here. Oh, maybe I did that. I think I did that when I was showing this a different context. Let me pull that up. Yeah, here we go. Okay, so this is an example of, okay, so this is a particular tiling. Okay, so this is allowing 0011. So this tiling, just to understand what this is oh, I need to evaluate this code. And we should turn this into a function repository entry. Oops, that's not enough code to evaluate. We need to, is this the code? Is this that same code, Ed? And does that include my code?
Yes, at least it was as of a couple days ago.
No, my code here for doing this hierarchy of tilings. Yes or no?
Yes, I think. Well, I haven't checked the last few days.
Okay. All right. And okay. So what this does is it takes okay, so let's take as an example the tiling. Let's take as an example this. I just want to make sure we understand what's going on. I want to take as an example this condition, this tiling condition here. Okay, so what this means is every 2x2 block of cells have to match those patterns there. Okay, and the big idea is that can be mapped into this condition. If we have an array, like a 3x3 array, that is just a condition on Boolean variables, right, Ed?
Yeah.
So for example, if we wanted to do this for more than 2 colors, we would have a more elaborate set of conditions. If we wanted to do it in 3D, we would have a more elaborate set of conditions, but I believe the same approach would still work, right?
I believe so, yes.
Okay. The big surprise is that it is possible to take this thing here and simply compute, take that Boolean expression and simply say for what values of the tile ij is this Boolean expression true, okay? And this is getting 4 instances of that. And so this is the mapping for each of these tiles, whether it's 1 or 0, right? And so that's then going to give us a tiling here. Right? Yes?
Yes. Mm-hmm.
Thank you. Okay. So now the question, so now you are going to talk about, so what I did was I worked out, okay, so this code here is code that tries to find the minimal, given this poset, basically. And I think I made some mistakes here in the way that I constructed this poset. But this code is not very long, and hopefully we can understand that. What I'm doing is I'm starting from single tiles, and I'm saying as I add tiles, I want to find the place where, okay, I've got n tiles, and I know what tiles. Yeah, I'm trying to add an n plus first tile, and I'm trying to find the configurations that first tile. Do you understand what I'm saying? Ed, do you understand what I'm saying?
Yeah.
Okay. Okay, so this code, what it does is, you can see here, these are the one tile tilings, okay? These are the first two tile tilings, right? These are the things where if what I need is the one tile tilings, and I want you to check the logic of this. The one tile tilings that don't tile, I've got the one tile tilings that tile, and then I've got the complement of these, which are the one tile tilings that don't tile. Make sense?
Yes.
Okay, so then what I do is, of the one tile tilings that don't tile, I try and add all possible second tiles to that. Okay, and every second tile I add, every tile that I add must be a tile that at least on its own doesn't tile, right?
Right.
Okay, so this thing gives me the minimal two tile tiling sets, right? Then I keep doing that. Now something goes wrong because I've ended up with, though this one came through okay, but in some of these I'm ending up enumerating. See here, I've got 215,000 tile sets, but yet the total number of possible tile sets here is only 2 to the 16.
Right. I don't see how that happened.
Well, it's a bug, right? It's a bug. So we have to understand how the logic is wrong. Okay, so let's take a look at what you've done, and then let's come back to understanding this logic. And then what I want to do is, we've got to prune the search space, and we can do that by using essentially the fact that given a tile, there has to be some compatibility condition to its neighboring tile, and we can already exclude tiles that don't have those compatibility conditions. Does that make sense?
Yes, for small cases.
What do you mean by that?
There's a combinatorial explosion for larger cases. So this won't work in general. This will work for small.
Did you listen to what I said, Ed? Did you listen to what I said?
Yes.
What I said was, the whole point is, the whole point is you can already throw out a large fraction of the search space by the fact that, given that you have a tile like this, if you are going to be able to tile, then it has to be the case that there is you should be able to remove that part of the search space without ever even considering those branches of possible tiles, because given that there are those two squares, for example, those two squares there, something has to be on top of them.
Right.
Okay, and I'm pretty sure we can pre-prune every set of tiles where there isn't anything that could go on top there.
Yes, that's called a patching strategy.
Okay, well, okay. All right, so let's take a look here. So you claim that there is a forbidden subset. What is this?
Those are all the forbidden subsets for the tromonos.
What is a tromino?
Three cells making L.
Okay. Okay. Well, I mean, but that's what I presumably will get in one fell swoop here, right? That's
right.
The first step there, right? Which, and do you have any different way to derive that? I mean, this is sort of trivially derived here. Right. Okay. So then what are you doing here? So then this is.
Those are all the cases for the 2x2 square, and it turns out there's 17 forbidden subsets, minimal sets that produce a tiling, and they
That's what
track with
that's what
yours.
I computed. Yeah.
Mhm.
Right. But I mean, so do you have a faster way to compute that?
No.
Okay, well, fine. So we're trying to make forward progress. So you're confirming that I got the right answer. Yes, I already knew I got
Yes.
an answer for this. Right? Okay. So do we have progress here? I mean,
Yes, the 2x3 is where progress is.
Okay. Did you figure it out?
I've gotten pretty far. I've got over almost 2,000 forbidden subsets.
What is a forbidden subset, and why are you calling it a forbidden subset?
It's minimal, and any larger set that contains it won't will have multiple tilings,
I
basically.
know, but why
There's
are
a
you calling
small.
them forbidden? I mean, they're minimal tiling sets. That's what I would call them. I mean,
Sure, that's a good name for them.
right. So we have. Let's be clear what we're trying to produce here. So I mean, if I go to the data repository, then I will find here that there should be something. What is the heck is that doing? Magnificent. Minimal inequivalent square tilings. Okay.
Yes, and those are for the X pentamino.
They're for the They're from the NKS book. Okay.
Right.
There are 171 of these things, and they correspond to. So one question actually is, what is the? Do we have in here the repetition periods for the tiles here, for the emergent tiles, if you understand what I mean, for the patterns? How do I deduce from the data here what the what is this tiling sequence thing here? Do you know?
I haven't figured it out yet.
And we didn't document it here. Well, maybe we need to look at the book and find out. But I mean, clearly, let's see. So we need to figure out the periodicity of these things, and that's a little bit non-trivial because they will not necessarily be square. They ultimately have to match together as squares, correct?
Yes, or polyominoes.
I see, with notches, squares with notches.
Yes.
Okay. Yeah, I think that's what this is all about, is the squares with notches issue. Um, uh, well, there may be an offset. Yeah, that might be the offset. Let's go find out what. I'm pretty sure there's a note in the NKS book about how this works.
On the next page.
There we go. So there are the 171 minimal tilings, and representing repetitive 2D patterns. How about that? Oh, look at that. Those are our numbers there.
Yes.
Okay. So this is, if I fill in this, okay. So this, wow, this is kind of funky. I see. So this is going to fill in a particular region. I wonder if there are better functions for this nowadays. But in any case, this looks like it is. I don't quite understand what that second piece.
This meeting is being recorded.
Do you understand this thing? Constraint sequence allowed tiles. No, that's not the tile set. That's the actual pattern. That's a representation of the actual pattern. And this is saying how to lay the pattern down. And what I'm not seeing here, what is constraint sequence? What does that mean? Or is that, let's read this thing in. Well, let's just take, oh, this is so pathetically done. My gosh. It's disappointing. It's kind of like I should do it all myself. I don't know why that's written as resource object like that, but anyway, let's take, maybe not the first one, let's take the 10th tiling. Okay, so allowed tiles, there's 6 allowed tiles because the constraint number here is, we can just take out the constraint number. And that number, if we go integer digits of that, that number is going to end up being having something with, guess what, 6, I'm going to claim. If we count the number of ones in there, it's 6. What do you know? Right? Does that make sense? That's the possible, of the 32 possible tiles, this is saying which 6 are actually allowed. Right? Does that make sense to people?
Okay.
You seem very surprised. Yeah, that's what that is. Okay, so now what is constraint sequences? I have a feeling that what that is the actual, is that the actual tiling? In other words, is that the actual thing? And we can determine that by taking this creature here. I do not like the name C that was used there. And I am actually going to do something. I just can't.
The shape of the tiles, according to the book, is a cross, five cells.
You're not getting the point. Look, the point is, okay. Do you understand? This is trying to show what the final tiling looks like. Do you understand what I'm saying?
I'd have to look at this code more.
No. You should understand this, right? This is, okay. This doesn't make a lot of sense. This particular thing here where it says 1022. Oh, maybe it does. 22. Okay, do you understand? This is a repeating block, right? This says how to lay down that repeating block in the plane. Do you understand what I'm saying?
Okay, yeah, that's representing the notches.
Yes, that's right. That's a notch. So I don't understand what the 2, 3 is, because this is a 3, 4 here. But let's see what happens if I say tile fill of this comma, I don't know, let's say 10, 10. That's not encouraging, is it? Well, that looks like garbage. It's a bad sign. So this data here oh, well, that's probably the problem there. There we go. Okay, so that is a region of tiling. You get what I'm saying?
Yes.
So there's a representation there of, so I don't understand where this, what the relationship between, see, I don't understand where this piece is coming from in this table here. Do you understand what I'm saying?
Mm-hmm.
right? And I don't understand what the tiling sequence is relative to that. Clearly, in a giant hack tower, I'm really surprised in the NKS book that I don't give the distribution of if I say this, comma, tiling image, okay, so I could always say image data of that. Oh my gosh. What on earth is that? You can't be serious. You just can't be serious there. It's got some weird extra 0.4 in it there. Okay, well let's go oh, this is horrifying. Okay, so there's the actual data from that. And so now how do we find out the repetition period there? Do you understand my question?
That would probably be the size of the notched rectangle.
I know that, Ed. I know that. I'm asking, given an image like this, how do you find the X and Y repeats? Right? It's some autocorrelation function that you can get by some list convolution, presumably.
Right. You connect up like.
Yes, I know that. I understand that. I'm asking, how can we actually do it with, find repeat or something like that? Or is that in fact too hard? And should we go back? I mean, clearly we've got something missing there because we don't have this tiling specification is not included in the data in here, which is bad. Did you see what I'm saying?
Mm-hmm.
Unless that's what tiling sequence is somehow representing. I mean, I can go back and look at my original code here. Maybe I should do that from whenever it is, 1992 or something. But we're going to do that in a minute. Let's look at your results here. Okay, what is this?
These are the minimal tilings known so far.
No, I understand. I understand. How did you get these?
I started with my original data and I found it had all sorts of mistakes when I started applying
No, that's not what I'm asking. That's not what I'm asking. I'm asking, did you use the modern SAT solver based tiling system?
Yes.
Okay.
Yes, and that's how I identified all the mistakes. This is after clearing out.
Wait. Where did the data? Wait. Where did the data come from? How could it have had mistakes? What are you talking about?
My original data, I didn't take into account notched rectangles. And so some of the tilings I created weren't actually minimal.
But, okay.
And then I looked at subsets and I basically did that recursively until I boiled down to minimal sets. And that's what's left here.
I'm sorry. Did you use the same procedure that I was trying to use, or did you use a different procedure?
I used a different procedure.
Okay. Do you believe that your procedure is better?
No.
Okay. Let me explain again what I'm trying to do. Okay. The search space using my procedure is too big. Do you understand what I'm saying?
Uh-huh.
And because there are a bunch of things that could be pre-pruned in what I'm doing, right? So at every stage, I've got the collection of tile sets that didn't make it so far.
So let's scroll down to the bottom of my notebook and we can go into patch strategies. So this is what my minimal sets are missing up above. These are not in my list up above. I basically found these by looking at patches. And patches are pretty much exactly what your method leads to. So you start with, say, a 4x5 set, you find all the tiles in that, and then find whether or not that's a tiling set. And
okay,
as you
let's zoom out for a second, okay? What we're looking for is unexpected tilings, okay? Tilings that do not just, are not just simple low period periodic tilings, okay? So any procedure we use must be robust enough to not notice things we didn't expect. Do you understand what I'm saying? So anything that involves some elaborate thing with notches and tilings and so on like that, where we assume the answer is out of it's not part of the story, because we're going to miss the things that we're looking for.
No, basically we start by looking at all possible 4x5 patches, say.
Yes.
And then once we've finished, we've completely explored that, then we expand what's unknown slightly on one edge, and then we keep on slowly expanding these patches until we've basically solved everything. That has a slow combinatorial growth.
What do you mean? I mean, we have a procedure with SAT solving that is fast for determining whether, given a particular tile set, whether there is a tiling, right? Now, what are you solving with respect to that? Because you don't need to resolve the SAT solver problem. We've already solved that.
Well, part of what you're creating is, say, a set of 6 tiles that doesn't tile anything yet, but for, say, 62 tiles, binomial 62-6, that's too many to play around with. When you look at the patches instead, it has a much slower combinatorial growth.
What are you talking about? I mean, okay, is it that what you're saying is that instead of looking, so in what I was doing, okay, the wherever it is, I am simply picking a fixed size, right? Wherever it is. A fixed size, it defaults to 50 here, to run the SAT solver on. Am I making sense?
Uh-huh.
Now, that size is tricky because it could be the case that there is a tiling, but its periodicity is larger than 50.
Right.
But I don't think, let's think, is this going to fail in that case? No, it's not going to fail in that case, because if it does not have periodic boundary conditions, right, the boundary conditions are free and empty. We specify nothing about the boundary conditions. So the satisfiability condition is still going to be satisfied, even if the periodicity is going to still say, yes, there is a tiling in this subregion, even if it can't match it to something on the outside. Do you understand what I'm saying?
Mm-hmm.
Right. So this is in fact a correct procedure, although it may be wasteful because it's trying to do 50 by 50 tilings when you say we could reject things on the grounds that they can't even tile a 6 by 6 region, for example.
Right.
Okay. But I think there's more pruning that can be done. So did you understand what I was saying about these matching conditions? Look, let's read what I wrote in the NKS book about this this thing. Okay, it's very short here. The number of constraints to consider can be reduced by symmetries. Clue. By discarding sets of templates that are supersets of ones already known to be satisfiable. Okay, that's what we're already doing. And by requiring that each template in the set be compatible with itself or with at least one other in each of the 8 immediately adjacent positions.
Mm-hmm.
Okay, so what that is doing is saying that that's a compatibility test, and there may be some easy way to do that logically, a compatibility test for each, which allows us to instantly reject. Okay, so the thing to understand is the procedure that I'm using, which again has some small bug in it, is something which is living at the edge of untilability. Do you understand what I'm saying?
Mm-hmm.
We don't have to worry about there being many solutions. We're worried about, we're saying, so most things we look at will have no solutions, right? So if we can reject, if we can say, see, the problem is once we have a subset, right, the addition of an element to a subset, yeah, we can know that a subset is going to not be able to tile very quickly by this criterion. Do you understand what I'm saying?
Yes.
That doesn't mean that a superset of that subset won't tile.
Right.
Okay, so the thing that I would like to ask is, in the poset here of all possible tilings, which of these elements fail with this criterion? Do you see what I'm saying? It still might not tile very far, but can we draw a version of this where we only consider those things which have first nearest neighbor compatibility? Do you understand what I'm saying?
Yes. Basically, it can cover a patch.
Well, I don't know. It can at least cover. Is it a patch or is it just, it covers some, go ahead.
If the tiles can cover some small region with each other, then they have some minimal compatibility.
Well, okay, but there may be an easier way for determining the immediate compatibility than actually looking at the tiling of a patch. But yes, the tiling of a patch is a criterion here.
Whereas something like an all white tile and an all black tile, those two alone are not compatible, and you can just throw that out.
No, but
because
do you
they can't cover each
do you
other.
understand? Do you understand? In this poset, right? What does that mean? That means there is a section of this poset where as soon as you've got, as we walk towards this, no. If we're doing minimal subsets, we also have to have the property that every tile has to be used, right?
Yes.
We can have that requirement. So assume in a minimal subset,
Otherwise, it's not minimal.
yes, exactly. Exactly. By definition. Okay, so that means that in our famous poset here, we can, as soon as we have two incompatible tiles in the subset, we can zero out, we reverse the arrows on this poset if we want to. We can zero that out. We're not going to make it. That's not part of our minimal story then.
Well, two tiles can be incompatible but still work in the same minimal tiling system.
Yes, okay, fair enough. All right, so but the thing I'm trying to understand is, with what criteria can we reject which pieces? I mean, so just to be a little bit more realistic with this thing. So, I mean, clearly the actual thing we've got, let's say we just do your tromonos, okay? Which is 2 to the 3, that's 8, right, of those things, right?
Right.
Okay, so we've got this creature here. Oh, for goodness sake. Yuck. Okay, let's try and draw that in a slightly less completely obscure way. Also not brilliant. Okay, this is our poset for the tromono. Okay, so in that poset, we should be able to label, given your results on which ones tile, we should be able to label in here the tiling threshold. Do you understand what I'm saying? Mm-hmm. Let's do it. Okay, so where is your set of tiling tromonos?
Up at the top.
And probably I can derive that as well. So, but you've got the minimal tiling tromonos, right? Well, which are the minimal ones? What are you doing here? Is this the subsets?
Yeah.
Okay, so this is.
So 0 is the all 0 tile, 7 is the all 1 tile, and so on.
I understand. So this is the digit sequence of the snaked tiles, so to speak.
Right, and I've got the code for tiles right above it.
I don't want the tiles. I've just got the numbers here. So I mean, I could do the same thing from 0 to 7 here, just to make it slightly easier, right?
Right, and it might be easier to leave out 0 and 7.
No.
Okay.
We're trying to color this thing based on. We're trying to do the thing that I wanted to do, which is show which section of this corresponds to a valid tiling and which does not. And this will be the frontier, right?
Yes.
Okay, minimal tiling cases. This is, okay, so this is post set for Tromino tiles. Okay, minimal Tromino tilings. Okay, there. All right, so now those will presumably correspond if we look inside here. If we let's do a smaller one of these just so we understand what's going on. Let's say to 3 here, and let's say vertex list of that. Okay, great. Okay, so here these vertices, we should color those vertices, right? And actually what we want to do is color every vertex which is a superset which contains any of these, correct?
Correct.
Because those are the things that tile, right? So then we want to take this thing here and let's call that Hassie. And let's say for that, we want in range 0, 7, we want subset Q. So what we want to do is we want to say graph of Hassie, vertex style, arrow, and then we now want to say if subset Q, is this right? If subset Q hash comma any of those. So if any true of the thing we're looking at, subset Q, we're going to need some variable here. Function. What are we going to call it? T or something. Okay, so what we're doing here, are you following this? Anybody following this? Okay. If any true is if it's true for any of these, wait a minute, help me out here. This is no. This wants to be this. See what I'm saying? So that's asking for each of those. Which way around is the argument? Are the arguments to subset Q? List 2 is a subset of list 1. Okay, so that's T comma hash. Is that right? Are you following? Anybody following here? Anybody?
I'm following. I don't know if it would have. I've never used subset Q myself.
Okay, is this correct? That's what I'm asking, right? Any true is checking, is this true? Are any of these subsets of the thing we are looking at, right? Do you understand what I'm saying?
Mm-hmm.
Okay, so then I want this, and I want that mapped over vertex list of G. And where do I have this wrong? That is that. And I want to close that. And let me do this. Vertex list. And I want to probably say Okay, why do they all come out white? Do you understand the question? Okay, so here, let's take a look. Subset to T. Okay, so the vertex list of Hasse contains a bunch of subsets. So let's try and take a look at one particular example of that subset. Okay, so we're going to take a look at the subset 2, 3, 1, 4. What did I do wrong here? Oh, I don't need the hash. %. Okay, so this says it's white. So it claims, so what's an example of something that contains none of these as a subset? None of
You could
these.
just
So
do
1,
6.
Well, we have a mystery on our hands. Why did this have everything white? Okay, let's look at the vertex list. That should be all subsets. How many of these are there? Yeah, it looks right. Okay, so let's just check this thing here. Map that. Oh, I think I may have made a stupid mistake. Okay, brilliant. Okay, so that is showing us of those subsets, which ones are, which ones are, oh, I see. You know what, we need to do subset, we need to do not subset, don't we? Because that will be the things, if it is one of these minimal ones, then it does tile. If it contains one of these as a subset, so it's a question of whether it's a strict subset or not.
Right. Uh-huh.
So in fact, what we want to say is not subset there. So now, what? Okay, wait a minute. Or is it, do we want to say none true? Okay, so I believe that's correct. I believe that contains, that is only those subsets for which there is no possible tiling, right? And that most sets of tiles do tile. Most trominos tile.
Could you
Right.
clarify your color scheme?
Well, red is supposed to be, it tiles. Red means it tiles.
Yeah, if it contains either 0 or 1, or 0 or 7, it tiles automatically.
Well, okay, so let's find out if that's correct. So if we're going, that's the null thing, and that's the 0 thing, I think. If we look at the list, the vertex list of that, it's going, the first subset is going to be 0, the null list, that's 0. So this looks promising. Okay. So, okay, so now let's go and insert this, and it's rather mysterious why. Okay, so let's hold on, let's put that up here. Oh, I see what's wrong. I see what's wrong. Silly mistake. Okay, there we go. Okay, so what we've got here in the Hasse diagram, that represents the untiling frontier, so to speak, for trominos. Does that make sense?
Yes.
So,
With the absolute bottom being nothing.
yes, there are no tiles allowed there. So this is 0 and 7. That's the 0 and 7 tiles. So we could label every one of these elements by a tile set.
Right.
Right. And that's showing which tile sets. So it's showing coming up from nothing. That's showing which which possible tile sets tile. Okay, so we fully expect there will be tentacles coming up. There will be untiling tentacles that might come up higher in some of these other cases because the frontier is the minimal tile set.
Right.
Right?
Could you give another color to the minimal tilings?
Yeah, I was thinking about that. All right, let's see if we can do that. Let's say, so we say if none true, blah blah blah. Let's, instead of the red, let's say if member queue of this list, this is a total hackosaurus. Is that the right way around for member queue? I should remember this after 35 years.
It would be easier computationally if you check member queue before you check none true, I believe.
I don't care, but I agree with you. It would be. But I was avoiding the fact. Never mind.
Comma T.
I did. I said comma T there. Right, and then if it is a member queue, let's call that blue, otherwise red.
Okay, yeah.
Okay, so there's that's actually not a very good color, but anyway, never mind. So I mean, this is stupid colors because really what we should have is green for tiling because it means it's go, and then yellow for, that. And if it doesn't tile, it should be red. There we go. Just like, okay, there's the traffic light mechanism. Okay, so there's the frontier, and that's the collection. Okay, so all right, so now what we want to do is, this is showing us my code is supposed to be by layers checking off, these are survivors at this layer, right? Those ones are already dead. These are survivors. And now we're going to add, how can there be something that goes directly from a no dice to a happy tiler without going through the frontier?
Because there's a yellow going to it.
Yeah, there's a yellow under it.
Oh,
because there's 0 and
right,
7s.
Right. But what that's telling us is, in my way of doing this, I'm following every edge, but I don't need to.
Right.
Okay. So, okay. So how do we not follow every edge?
Forbidden subsets.
What does that mean?
You basically forbid 0 and 7 forever once you've determined that it's a minimum.
I know.
Tiling.
That's exactly what I'm doing. That's exactly what my code is doing. But there may be a more efficient way. I see what you're saying. When we generate the next set of subsets, what I'm doing is I'm generating all of them and then removing some. Okay? So if you've got a way to generate subsets so that you never generate a subset that contains certain, you never generate a subset which has as a subset one of the forbidden subsets. Do you get what I'm saying?
Mm-hmm.
Okay, so at each level, want to generate only the new subsets which don't contain any of the already forbidden subsets, smaller subsets, right?
Right.
Okay. So is that, if we succeeded in doing that, would we have a minimal algorithm? Okay, the other issue is symmetries. Right? We don't have to consider, I don't know how easy that is to implement. And I don't know how big that reduction is going to be. Is that obvious to you? I mean, I think you have to have a symmetry of the whole tile set.
I decided not to bother with it.
Well, let's just think about it for a second, okay? So clearly there's, given the symmetry of the underlying tile shape, right? There is a symmetry that applies, but it has to be applied to every tile together, right?
Right.
Symmetries apply to complete tile sets. So if we know that it's the group of the square, for example, we can reduce the complete tile set by, we can find, we can mod out by the group of the square.
Let me show you a bad example. It's down at the bottom of the notebook. It's basically the dominoes that are surrounded by white. It's right at the very bottom. But they're all equivalent, but they all have different tile sets that generate them, and all the tile sets are minimum. But even though the tile sets are all completely different and minimal, you're basically just getting the same thing over and over.
I don't care. I mean, that's fine. Yes. Okay. So that's interesting. That's an interesting fact. That note different tile sets can give the same minimal tiling. Right? And I wonder whether I accounted for that in that 171. I think I did not account for that in that 171 things in the NKS book. That is, I think I showed only the minimal tilings, not the tile sets, if you understand what I'm saying.
You've got the page, so let's take a look at it, because it would be obvious if it might be that the 5-cell tiles you use.
No, I mean, these are all distinct tilings, right? I mean, there's that creature there. And that, I think I say in the caption what was done there. I mean, we can also look at
these look appreciably distinct.
Look, it's very clear what it says. If none of these 171 patterns satisfy the constraint, then it follows that no pattern will satisfy the constraint.
Okay.
Okay.
Also, we're still working on a hypercube. We should be able to remove identical permutations. It doesn't matter what order the tile set is in.
Nor does it matter here. This is subsets. So all these subsets are being canonicalized. They've all been sorted.
Right.
And I don't think this Hasse diagram better not be a full.
It's not. There isn't orderings in there.
Okay. Okay. All right. Let's go back now to where were we? Okay. I think what we should look at now is a better version of my code, right? Except, so let's try to understand what. Okay. So this is the code that I have here. Let's see. All right. Let's go back down here. Iterative addition of tiles, basically. That's what we're doing in this code. All right, let's take a look at what this is doing. All right. I wrote this only a few days ago. Okay. Actually, the other thing I should put in here is I should put something in which allows it to flow through to the satisfiability instances, the number of instances which need not be fixed. In other words, it's looking right now for a single instance. Am I making sense?
Mm-hmm.
Okay, all right. So let's take a look at this code here. Oh my gosh. Okay, tiles is the original set of tiles. Okay, the original set of tiles we're working with. So for example, here, this is, let me go ahead and launch these computers so we have them to run.
I could suggest an experiment.
Okay.
Grab one of those items on the notebook underneath and just remove one of the numbers, and your system should be able to find what was missing and add it.
What are you talking about? I'm sorry. Look, let's just look at what this is doing. So let's look at your trom example. Okay. So your trominos will be of the form. I mean, in fact, I think I have ones down here that are of that general type. Here we go. Okay, so to make your trominos, we would do blank, we would do this, correct? Is that correct, Ed?
Yes.
Okay, so then my code will be, take this. Okay, so here I want to say 8 for reasons that will rapidly become clear. Okay, there we go. All right, so let's look at these numbers here. Okay, so those are the numbers of survivors. Am I making sense? Okay, this is the complete tile sets. This is the analog of your forbidden tile sets.
Okay.
Right? Make sense?
Mm-hmm.
Those are the minimal tile sets. So here, what it did was, at the first level, it finds those. Okay, so it says that then, so there are 8 of that first level, right? Corresponding to the single, did you get it? Follow the single tile pieces. Okay, then it claims there are 21 that come from the 6 survivors here.
That makes sense. Mm-hmm.
Why is that obvious? 6 survivors, and then I add in all the other, of those 6 survivors, I'm adding in the 6 survivors there, then that would make 36. But then I'm pruning somehow. I'm sorting, I think. Oh, I see. I'm probably removing the diagonal. Right? Do you understand what I'm saying?
Yeah, I'm just checking something. And
okay. All right. So that's what my code is doing, or at least is supposed to be doing. Okay, but we may be able to vastly prune that 21 or that 38 or whatever down here. Am I making sense? That's our objective. Please pay attention here.
Mm-hmm.
Okay, so we're going to read this code and we're going to figure out whether it's actually doing the right thing. Okay, because let's take those numbers. Okay, we can do it in a very low tech way, or we can do it, let me do it in a slightly higher tech way. Let's say, well, here. Okay, who knows how to do this with a @star? Is that right? Anybody know if that's right?
I have no idea.
And let's reap the results of that. Let's check that that works. Hold on a second. F @star G of X is F of G of X. That's right. Okay. I gotta learn to use @star more often. Okay, let's do this again. Let's see if our technology works. Yes, amazing. Look at that. Technology at work here. Okay. Okay, that seems to be completely crazy because the number of, there are 2 to the 8. No, how many possible omino things are there here? Tromino things? There are 8.
2 to the 8.
Yeah, so that's crazy. So something went wrong here. Do you understand what I'm saying?
Uh-huh.
Okay, so our mission is to figure out what went wrong, right? Because it's over-generating those cases.
The last case is 216. Is it possible to just look at the list of all of those?
Sure, but let's see if we actually that's a very suspicious number. I don't think we should do that. I think we should read the code first for a second because it may be really obvious what's going wrong. I wrote this quite quickly. Okay, so let's take a look at what it thinks it's doing. Okay, so it says so far, these are going to be tiles, the so far tiles, otherwise known as already. I believe this function is the one that is trying to append. Yes, look at this, look at this, look at this. Here's what it's doing. It's appending each of the tiles, right, onto tile tuples. Tile tuples is the survivors.
Right.
Okay. And already, tile tuples is the survivors of ones that didn't tile. Do you get what I'm saying?
Uh-huh.
Okay. So already is ones that did tile. Am I making sense?
Right. So maybe a union around the catenate?
Which catenate? This one here?
Right.
Isn't it going to need a sort, a map of sort as well? But why does it need? I think it's going to need it. Well, let's try. We can certainly try that. I'm a little surprised that it doesn't need. Oops. Okay, we can try that. All right, let's give this a whirl again.
Same numbers.
Didn't make any difference. Okay, all right, so let's get rid of that. Well, okay, let's just try to understand what that was doing. Okay, let's get rid of that for now because it didn't make any difference.
Mm-hmm.
Okay, let's look at what this is doing. So at every, it's taking tile tuples. What does it do here? It calls.
Oh, maybe put union around the append. That way you're not appending a tile that already exists.
I see what you're saying. Well, then I probably need. Then I will need the union around this. Mm-hmm. that's a little odd. Why is that smaller than 256?
Maybe because things got thrown out.
Yeah, things got thrown out. It didn't need to have that many. Good work. Okay. Well, that's not wrong, right? That's definitely not wrong.
It's definitely working correctly for the Promino case.
No. But the general idea here is not wrong.
Mhm.
Right. Okay, good. All right, let's try a less trivial case then. Let's try the 2x2s. Okay. Let's see what happens there. Okay, 2x2s, here we come. And then the question is, okay, for the 2x2s, actually I could generate, okay, here we go here, the 2x2s.
I'm not sure if I might not be interpreting this correctly, but I'm not sure if the the stuff earlier is necessarily minimal.
That looks correct, though.
Let's see what it's doing. Okay, so it's gradually trying to add another tile. So let's see what its total is here. Well, so long as we didn't miss anything, we've achieved, so 2 to the 16. So we've achieved a substantial savings there.
Mhm.
Let's just, for fun, let's take these tile sets here. Okay. And let's color a Hasse diagram for with this tile set. Does that make sense?
Okay.
So in your notation, then, we are going to turn these into, we're just going to flatten each of these, right?
Yeah, flatten and integer from digits, from digits.
Okay, so we concatenate this, and then we're going to do a from digits of flatten of hash, comma 2, that. Okay.
No, something's wrong.
No, that's not what we want. That's not what we want. What we want is, oh, for each, no, we don't want this flatten. We want a mapping of flatten. We want to map this. We want to map this at level 2. Okay, does that look convincing to you?
Yes.
So those are our tile sets that are, those are the subsets of the right. Okay, so those are, okay, so now let's take our Hasse diagram for this guy. Oops, where is our Hasse diagram? Now, this is going to be much more of a mess, but nevertheless kind of interesting, I think. I mean, we could also figure this out just by, we can also make a different kind of diagram, which is just showing how many tile sets. I mean, here, the very naive thing we could do here is to just say counts length slash at that, and then make a bar chart. I see. That shows the number of minimal tile sets of successively greater length. Right? And so then, in this case, we will be doing this thing. This is, let's say, Hasse 4, is this thing to 15. It's a slightly big creature. And then here, oh, very big creature. This may not be such a smart idea. Well, so much for that. All right, it's mostly going to be, forget it, it's too much of a mess. It's probably spending all that time trying to do the layering, the layered digraph embedding.
Probably.
Yes. All right, let's kill it. Okay. The good news is it aborted.
I think
Okay.
you missed one of the Hassies in 171.
So I did. Thank you. That would have definitely made it fail. But okay. All right. Emboldened by our experience here, let's try another tile set.
I think we should try the five cell case in NKS, the X pattern.
All right. But then I want to try some other 5-cell cases. But okay, fine. We can try that case. So let me see. How do we do that? We want to do, in this case here,
or the 4-cell trauma node, similar to Rule 30.
All right. Well, let's try a 4-cell case first. Okay. Okay. So help me out here. So we want a 4-cell guy that is #1, #2, #3, blank 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 #4. Correct? Does that make sense?
Yeah. Mm-hmm.
Okay.
Yes.
Okay. All right. Okay, fine. Let's try that then. Okay, here goes. Stripes and spots. Now, some of these may be, in fact, equivalent. I mean, some of these are equivalent under symmetries. I mean, I don't know. Have we seen those spots before? No, we haven't.
Yeah,
So
I think these are different than the 2x2.
No, I understand that, but I'm asking a different question. I'm asking the question, is it possible for us to get the same pattern more than once here?
Yes, looks like it.
Well, are you sure?
Oh, we're getting new material. Okay, we're getting behavior I haven't seen before.
Oh, and we finished already. Wowee. Okay, the 5-cell case. So one thing we're seeing here is everything's periodic, right? These are all periodic patterns.
Mm-hmm.
So let's try something where we, for example, separate off so we can clearly do 4-cell cases with ease. So let's try one where we've separated it off a bit. Do you understand what I'm saying? Where we make a more random. Can you make a suggestion for how to do this? I want to arrange the constraint cells to be in a more random pattern.
You could do the Z tetramino.
Okay.
1, 2.
I'm not personally acquainted with these 2
at the top, shift, 2 at the bottom.
Okay. All right. Okay. 2 at the top, shift, 2 at the bottom. So that wants to be #3, #4, right?
Yes.
Okay. Okay, our friend the Z tetramino coming up. Stripes and spots. That's a slightly interesting thing. That's a seam. I don't think it's a necessary seam. It's not a necessary seam. I bet if we had more satisfiability instances, that seam would no longer be there. Okay, so in fact, we have fewer. I think we have fewer possible tilings with this Z case than in the other case.
Mm-hmm.
I wonder what happens if we just distribute the things sort of randomly, just sort of like little probes. Like imagine an animal with tentacles where it's just probing particular places where it isn't, where the things are not compact like this. Okay, so let's say we do something like this, and then we say that #2, that. You see what I'm saying?
Uh-huh.
What if you just did all the 3x3s with a cell in each corner?
We can try that too.
I'm curious to what this one will do, though.
That's kind of more fun.
Definitely getting stranger.
Okay, not that exciting, but more possible matches. Okay, let's try suggestion of ones at the corners. I probably should just, yeah.
For that one won't work well for checkerboard reasons.
What do you mean? You mean it's just going to make, okay, hold on. So you're saying this is going to be equivalent to a smaller one.
It's going to be equivalent to 2 different tilings.
All right, well, when in doubt, just let the computer work.
Right.
Mm-hmm. I agree. It'll be 2 interpenetrating, so to speak, checkerboards. Oh, they're rather pretty. Look at that one. Look at that one.
Mm-hmm.
Is that a seam? What is that going on there? Okay, hold on. Let's wait for it to finish, and then I want to go look at that one in more detail. Okay, hold on. Okay, let's pick up this one here. And let's say generate. Do you remember what the function is for generating tilings here? I think it's generate tiling. Okay, so in this case, we're saying generate tiling. We're going to have no initial seed. We're going to have size, let's say 30. And let's say we want to generate 3 instances. And then for each of those, we want to do tiling state plot. What is going on? Boring. Okay, what happened there when it was smaller? Wait a minute, is this the same one? Oops, it's up here. Okay, I don't understand what happened here. This is the one, right? Yeah, it's that one.
Mm-hmm.
How big are these? What did I pick as the default size for this? I picked. Oh, I'm pretty sure I've been doing 20 now. Find tilings. What does the 8 mean? Oh, that means up to the size. Okay, so that's a 20. So now let's take a look at the 20 here. I'm very confused by this. Let's omit that. Okay, that's really weird. So that is showing a misshapen creature there. Okay, but now if we keep going here and we generate 4 satisfiability instances, oh, I see. Basically, those must be some kind of boundary effects. Ed, your comment?
Right. Yeah, I don't know why that's happening.
Okay, all right, let's keep going and let's go on to look at the, let's consider the case, the next case, unless we want to do another one of these, let's go ahead and do a 5 case.
Okay.
Okay. I'm a little concerned about this because obviously it's going to be, should we do a notched? Well, let's just do the real case. What the heck? So that would be blank #1 blank #2 #3 #4 blank #5 blank. Now, is there any way we can prune down that list?
I don't think so.
There's no symmetry argument here.
There is, but I think that is more trouble than it's worth.
All right, here goes. If we have to, we'll run this on a slightly bigger. I mean, I've got 200 and how many cores do I have? I have
Last I saw was something like 500. Oh,
156 cores running right now. We can run this on the cloud.
I don't think you'll need to.
Okay, hold on. This is 8 was the one before. That was, hey, wait a minute. Well, actually, they'd all finished by the time, right? They'd all gotten to zeros.
Right.
Yes, I didn't need to run it any longer. But if I could have run it longer, 8 wasn't the correct thing to do for this 4 case. You see what I'm saying?
Okay.
Right? Did you understand my point? It's 2 to the it should be 2 to the 4. It should be 16 in that case.
Okay.
I just want to run that again just to check what happens if I make that 2 to the 4 there. Okay.
Okay.
Just to check that nothing weird happens, because what should happen there okay, so now these are still growing. I'm a little bit confused by that. Okay, so what we're looking for is 2 to the 2 to the 4 cases, less than 2 to the 2 to the 4 cases, right?
I think it's because you used union above. I think that you just want to disregard it if there are any duplicates. You don't want to compact the duplicates together.
I don't understand that comment. Do you think, is this answer correct or not? I mean, in other words, what are you here? This is the number of survivors. So there are 4274 that never managed to tile, and adding more tiles to the mix doesn't affect that. So that's
I think that number should go to 0.
I kind of think that seems right too. So let's understand why it doesn't. Okay.
I think it's a problem with the change we made above.
Which change?
When we put the union around the append in line 162.
No, that's not wrong, because that's taking. No, that's a different problem. Look, the problem you're referring to, Ed, do you understand what Joseph is talking about here? That is, should there be a set? What we've got here is a set that hasn't tiled, right? And what we've done is we're ascending into the green area here. And for some reason, we're leaving over a residue of ones that we're still considering. And that seems to be wrong to me. Do you get what I'm saying? I need a piece of chocolate. I will be right back. Ed, can you think, please? I mean, yes, I think there is something wrong here. In other words, as we ascend into the green, we should have given up by now.
Right.
Right? I think there's something wrong with the way that we're removing this thing here. Is probably not enough removal. We need to remove more than that. I'll be right back.
Okay.
So what exactly happens if we, if in the thing where it's mapping on two tiles, if we try and add a tile that's already in the set?
Then it's appended, and then the union removes it again.
Shouldn't it be? Okay, and then what is it then added to?
I'm not sure.
I think this code is quite complicated. I'm not sure if I understand it in its entirety.
I agree. Using the seed values might be helpful though, because that way, if we have a patch that's covered by, say, 6 tiles, and we add another tile, we can use that seed as part of the system. Of course, it might be that there's a bad patch that can't be further tiled. I'm not sure how to.
Okay. Did you figure out what's wrong with this code?
No.
Were you looking at? Okay, let's go start figuring out what's wrong with the code. Okay, so here, this is attempting to add a tile in. This is saying add tiles in all possible places to the current set of untiling tiles. Right, guys? That's what that's doing.
Yes.
That's the current set. That's adding a tile in all possible ways to the current set of untiling tiles. Okay. Now, what we then want to do is to select from there any from the current set of untiling tiles. See, one of the things that I find mysterious is why are there any untiling tiles by the time you get to this level? Do you see what I'm saying?
Mm-hmm.
So that suggests, let's take a look at where tile tuples methinks I see a bug. Yes, look. This is saying I think what's happening is that we're picking up all the untiled tile sets so far. See what I'm saying? Whereas we don't need to do that. We only need the ones which are one size smaller. Do you get what I'm saying?
Right.
Okay, so this is now, okay. Okay, like pay attention here because okay, that's the original tiles. So this is somebody, yeah, whatever. Okay. Do you understand what this is doing here? Do you understand this?
New tiling 0.
Yeah, new tiling 0. Okay. Okay, here's what's happening. This is finding the tiles that somebody is, please, could you either put yourself on mute or stop, whatever. Okay, so what this is doing is it's trying to do a tiling here, okay? For each of tile tuples, this is trying to generate a tiling. Either it finds a tiling or it's a failure, right? If it's a failure, so in the end, new tiling 0, yeah, find tuples, yes. The failure cases are first of W are the failure cases. Does that make sense? That is the things in the tile tuples that didn't, the things in tile tuples that didn't tile are first of W.
Okay.
Or maybe that's the ones that did tile. Hold on. Hold on. I got to read this code carefully. No, these are the parts that did tile. So far is the things that did tile. Okay. So those are the ones that have tiled, right? Those are the ones that did tile. So now what it's saying is, at every stage, if what we've got here is now a subset of one that already did tile, but those are the minimal tiles so far, I think. Okay. What? Do you understand what I'm saying?
I think so.
Maybe, Ed, maybe you should take this as homework to try and debug this. Okay, I think that this is right. So I think what's happening here what this is doing, let me explain again. This is globally for all tile sizes. Okay.
So what are so far and already?
They're the same thing.
Are we keeping minimal sets anywhere?
No, they're just being generated.
Maybe we should take a sample of the tilings. It's still trying to check after it's found all of the tilings.
Yeah, that's a reasonable idea. So let's go ahead.
Also, we should eliminate things that have minimal sets as a subset.
Okay, well, let's look at this here. Okay.
I think it would be safe to run the order 5 case to like 8 levels.
Okay, well, all right, that's all right. Okay, let's do that, and then let's figure out what's going on there. Look, actually, it seems silly to do that because I think there may be a simple bug here. Okay, let's go ahead and instrument this. And what we want to do here is we want to say echo function of tiling state plot /@ #. Do you believe that? Okay, so let's do your Tromino case here. Oops, wrong thing. Oh no, sorry, that's wrong. I shouldn't have done tiling state plot. I should have done wait a minute, what's happening here? Map tiling that plot at level 2. Try that. What's happening here? Why isn't this
I think you
working?
dropped the ampersand.
You're right. Okay. So those are, I see. So what that's showing is at every level, it has preserved yeah, it's got a complete map of everything it found so far. But I don't really understand why. Doesn't it need that? As it adds elements, does it guarantee not to add? Once one of these has been a subset of something, it could still become a subset again, couldn't it? I don't know. What's that?
No. Once it's been established as a minimal tiling set, it's not a subset for anything that matters.
Explain.
For example,
look, as we add another candidate, it might just tile now, tile set. We need to complement it against all of these things, don't we?
No, for example, take the all black set. There's no point in adding anything to it.
I know that. We've removed that.
I don't think we have. Because it looks like we're trying to add to the existing minimal tiling set.
Ed, this is not what we're adding. This is what we're subtracting. If this ever showed up again.
Okay.
Right, because we're adding tiles one at a time.
Can we take a look at what's being operated on?
What do you mean, what's being operated on? You mean
because
that
because we're doing 24 things each step, but we can't take a look at what those things are.
What they are. Okay. So where I want to do it. Sorry, never mind. Hold on 1 second. Okay, here goes. Wait a minute. Why is this? Oh, these are tile sets again. Never mind. What's going wrong here? Tiling pattern plot. Okay, what's going wrong? Can you see what's going wrong here?
No, I don't use echo functions that often.
No. That's not the question. Tiling pattern plot.
Looks like you're ending up mapping it on a layer that's too far down.
Yeah. Okay, here we go. So now, what are the 24 survivors?
Oh, it's not getting rid of the survivors.
Oh, look. These are the survivors here. Now, what should it be doing there?
Once it's considered a survivor once, it shouldn't consider it again.
Is that right?
Yeah, because adding one tile to a survivor and then doing the same thing on the
By
next
survivor,
step.
we mean something that didn't tile so far.
Right. But it looks like these are the same cases each time.
You know what? You're right. You're right. So the issue here is that append to there which is accumulating those. I think what we want to do is just this. Let me just try this. Hold on one second. Let's just make a copy of that. I think there's a good chance that it is just this. And there's no append to.
Uh-huh. I agree.
You know, the theory is, oh, wait a minute. This is going to return. Yeah, look, I think the correct thing here, we do want that so far because that is the minimal tile set. But we actually just want to feed this into here potentially. All right, let's try that. And it's, what the heck is all that stuff? No, it's completely broken. Nope, it's completely broken. Okay. Wrong. Okay. Ed, why don't you try and debug this later?
Okay. And I did have one more thing to show.
Well, hold on one second. Let me just rerun this so we don't have garbage here. Okay, I want to try doing the bigger case.
Mm-hmm.
Even though we know this isn't the right thing quite. Okay, so let's do 8 levels here. It's getting big quite quickly.
Right.
So that's 30,000. We think that's 30,000 survivors.
Right.
That we have to check.
It might be faster with patches and seed values.
Well, why don't you try rewriting this code to use that? Okay, where you generate a patch. I mean, what you're saying is you're generating a patch and then you're seeding from the survivors. Is that correct?
Yes.
I mean, this code has the possibility of seeding.
Mm-hmm.
Right, so I think that's a good idea. Oh, that's going to take forever.
Which level have we gotten to?
4, 5.
Okay.
No, I do agree that the patches and seeding is probably not a bad idea. Although it should be done carefully.
Right.
And by the way, we should turn these into some function repository functions. Okay, you said you had one more thing we can, well,
yeah, at the very, that opened up that thing at the end of the notebook. This is a non-periodic tiling system that can be forced using overlapping tiles.
Does it make a nested pattern?
Well, it's a non-periodic nested pattern, yes.
Okay, fine.
And then those two shapes there, I believe with overlaps, those force the non-periodic tiling.
So what? Why is this? I mean, given that we know that Penrose tiles already do this, why is this interesting?
Because you're looking at overlapping tiles. The Penrose tiles by themselves just do one layer. Your overlaps are doing multiple layers. So
I
this
see.
is
I see. So this is a thing where this is a tiling system where looking at the neighborhood of these things, it forces the neighborhood forces.
right.
You're saying you allow certain neighborhoods. Which neighborhoods do you allow?
Those two.
Which two?
Scroll down a bit. The two next to each other, those two neighborhoods there.
My gosh. So you're saying the fact that they touch at a tip is just confusing, right?
Right, right.
Okay. All right. So you're saying that given these two neighborhoods, if I look around every tile, like if I look around every one of those guys there, then I have either this version or this version with three colors. Is that correct?
Right.
But the colors aren't. I see. The colors are just labeling the type of tile it is.
Right. The size of the tile.
Right. But so what is the picture of the big one, of a big such tiling?
Down at the bottom. I guess you need to run the colors all points a little bit up, and there's right there.
Well,
Down a little bit.
Hold on. I think we have to kill this one. Oh, it just came back.
Oh.
Boring. But it did come back. Let's see. See if I can get it to. Oh, it did abort. Okay. Joseph was keen to try a pentomino. Well, let's try one more. Okay, I want to try this, but let's try one more pentomino. What pentomino would you like to try?
So take the cross, but shift the top cell over by one.
The F pentomino. And we could just, oh well. I was going to suggest 5 layers. Yeah, this is going to be equivalent to the X.
Why?
Because it's basically downwards growth.
So you're saying, I mean, these numbers are the same as the X.
I believe so.
All right, let's kill this one. Let's look at your. Oh, the problem is when you're running on many different machines, killing, it's not so easy to tell. Up. How could it still be running? How could it still be running here? I just told it to stop. Okay, now it stopped. It wasn't listening to me before. Okay, so here
the line starting with colors down a little bit. There. Just run that. No.
Okay, so now
and then the bottom one.
The very last one.
Yeah. There's a larger case.
And what's non-periodic about this?
These tiles are not in a periodic pattern.
They look periodic to me.
They're semi-periodic, but
can I make a bigger one? How do I make a bigger one? Just change that. What do I change? Change the 16 to something.
Try 18, I guess. I'm not sure whether I've pre-calculated it that far though. You could try it. Okay, I didn't calculate it that far.
Well, but how do I calculate it?
Oh, with it's actually a little bit involved. It's part of the algebraic tilings function.
But so
you could just stretch that one larger.
Doesn't really help me. What? Okay, so you're saying, I mean, oh, I see, and then it does something different here. But I
Right.
should be able to take this, and I mean, is there some substitution system that will just generate this nested pattern?
Yes, it's up at the top. There it is there.
It's slightly obscure.
Mhm.
I don't quite understand what it's doing as it flips around here. So I don't understand what this is doing, because how does it do it? Is it updating? Is it replacing a single tile by a cluster of tiles, or is it doing something?
Yes, it is basically using the rule that's read above it over and over again. It's replacing a tile with two smaller copies of itself, scaled by the super golden ratio.
Wait. There's two tiles here and there's three tiles here. So how does every tile replace itself with more than one tile?
The largest tile is replaced each time by two smaller tiles.
Okay, so and this thing flipped itself around just for
Right.
fun.
Mm-hmm. Yes.
I see. Okay, so here now, still the largest tile is the blue one.
Mm-hmm.
But so it's always the blue one that's getting replaced. Is that true?
Correct.
Is that not true? Okay.
Because it's recolored to blue.
Oh. But it's always the one that's, there are two shapes here, aren't there? How many shapes?
There's three shapes. It's all the same shape, but there's three different sizes.
Oh. Okay. Three shapes. Three different, I mean, one shape, three sizes. And so the non-trivial fact, how many shapes?
It's
In
only one
terms of-
shape.
No, I understand. What are other cases where you can tile the plane with a shape and a different size of the same shape? Clearly with squares, you can do that.
Right.
Are there other non-periodic tilings? Are there non-periodic tilings where there's
Yeah, I did a whole blog article about them. I found all of them.
Okay, that's cool.
And there's a whole bunch that no one had ever seen before.
Can you give me a link to that article for a second?
Look for shattering the plane. Yeah, there's this whole big family of tilings that no one had seen before.
Lovely, Ed. See, with context, it makes me care about these things. Without context, I haven't a clue. Huh.
And then after I wrote this blog article, I found even more.
So it's time for an update to it. Well, very interesting. All right, we should wrap up here. Someone needs to send Ed, maybe Joseph's interested too, can send them this file, which will show up on in the public thing by tomorrow, but can show it up, send it today. We've got a little bit of debugging to do, and also Ed's seed-based, thing. And then, the thing we really want to do is to look for other, I think there are other pentominoes to look at, and then we are on to the hexominoes, or whatever they're called, in terms of the of the tilings we want to look at. And my guess is that I think we're going to find a non-periodic one by 6, and we might even find one in a differently configured 5. So that is the objective. All right, well, thanks to folks I notice, oh gosh, the questions about metamathematics on here from Ryan. Different topic, sorry. I might have talked about metamathematics today, but I didn't. That's another thing that I happen to be looking at right now. Yeah, there'll be interesting things to say another time about the space of all mathematical theorems and its relationship to physical space. All kinds of,
I just realized the solution.
yes.
The checkerboard clued me in on it. You could set up a patchwork like that, such that you get different size grids which clash, and set up something so that one will not correspond with the other. So basically, you have a Paisley checkerboard and a non-Paisley checkerboard, and when you push them together, you'll get something non-periodic. It's a cheat, but it would solve the problem.
But how is that forced by a particular tile set?
I'm not sure, but basically you'd need two that are completely non-compatible. And for example, something on hexagons would probably work.
Yeah, okay, that's okay. So there are two other things here to generalize this. One is we want to look at the 3D case, and the other is we want to look at the hexagonal tiling case or triangular tiling case. But if you can see if you can fix this bug, that will be a good start. And then clearly the code is easily generalizable to it should be easily generalizable even to the hexagonal case. And I have to go to a completely different meeting.
All right.
Thanks all for joining, and see you all soon.